introduction to dynamics. And in fact, I want to make it clear that although there are differences between us, they are matters of perspective and not of substance. And I think that a large part of what I'm going to say can be considered as a reinterpretation, or at least an alternative way of expressing some of the fundamentals that he so eloquently described in his workshop and in his first lecture. So I've outlined what I'm going to say today in terms of these differences in perspective. And the first one has to do with this action perception cycle, which is a basic way of looking at the nervous system in which the two of us are in close agreement and differ strongly from the standard view which the great majority of my colleagues in neurobiology hold, and I think also the great majority of colleagues in his field of cognitive science. They also hold to an alternative view, which is basically a feed-forward kind of description. And I'll come to that in the first part of my talk. Our difference essentially is he's working from action through perception, and I'm going from perception through action in the opposite direction, so to speak, or at least to the different starting point. It's more like it. And the second element I'm going to take up is this hierarchy of attractors, in which Bill starts with the point attractor, goes to the limit cycle, and I expect we'll sooner or later have to take the step to the chaotic attractor. I want to go in the opposite direction. I want to start with chaos, because that's where things begin. And it's much easier to go from a chaotic cycle attractor to a limit cycle attractor and then to a point conceptually than it is in the opposite direction. And the third thing I'm going to take up is the difference in the prime organ access into the nervous system. I want to choose the nose, whereas he is working with the eye. And I'll show why that's the case. And I want to try and convince you that, in fact, the way in which the mind's eye operates is very much like that way in which the mind's nose works. That the differences in terms of pre-processing, yeah, they are substantial, though only qualitatively, not quantitatively. No, quantitatively, not qualitatively. But fundamentally, olfaction came first, and vision muscled in on an already going enterprise and adapted it to its own purposes without changing the fundamentals. So that, in my view, you won't ever understand vision, or audition for that matter, until you understand olfaction. And then the final point I want to raise is the differences in the laws of dynamics, that those neurodynamics are not the same as those of psychodynamics. They're complementary, to be sure, but they have a different experimental base in terms of the kinds of measurements that you make of behavior versus those that you make by actually looking at these patterns of electrochemical activity and magnetic activity inside heads. Now, this first step of action perception cycle is really a statement that we have what's called circular causality in terms of the interdependence of the organism with the environment. And that now is a fundamental aspect which really distinguishes us, as I said, from a great majority of our colleagues. And that means then that if you look at the way in which brains are self-organizing, you cannot explain them in terms of linear causality. You have to invoke the relationship of large-scale systems to the components that make those systems and by which those components are influenced. So the simplest way of conceiving this has been done in terms of one of the key architects of this mode of thinking about dynamics, Hermann Haken, who talked about the circular causality in the laser. that the atomic particles have a degree of individuality, autonomy, which creates chaos. And as the energy level is raised, you reach a threshold in which there is a coalescence of some kind, and the interactions become stronger, and suddenly there's this state transition, what Bell referred to as a bifurcation. A transition from one state, in this case low energy and chaotic, to another state, a high energy state, which is in fact a limit cycle in that case. Now, that transition involves the cooperation of immense numbers of particles to create an oscillation of energy which is coherent, but which now enslaves or entraps all of the particles which are making it. That's where your circularity comes in. And you cannot go from any small number of particles to account for the wave and then back again. These things coexist. And that essentially, as I see it, is how brains operate, and particularly sensory cortex operates, by large numbers of neurons autonomously firing chaotically with a very wide range of frequencies, can, if their energy level is raised, will undergo a state transition into a coherent oscillation. And that's what we see in what we call gamma activity in the EEG. And that gamma activity acts back down onto all the neurons in an area of sensory cortex, visual, auditory, olfactory. They're all alike in this respect, and organizes them into some pattern. And that pattern will have the form of a spatial modulation of the amplitude of this common oscillation. Just the way a black and white laser picture is a common oscillation, but with an amplitude modulation over space, which gives you the light and dark. That now essentially is the way in which you go from a chaotic attractor to a limit cycle attractor. And I'll show an example of that from the olfactory system, and then another from the visual system. Now, the fact that this is chaotic does not in itself imply an excess degree of complexity. In fact, it can be, in some respects, rather simple once you get the hang of it. This is essentially, again, a change in perspective. One of the features that, or one of the kinds of behavior that I recall seeing in a videotape made by an entomologist, Bob Full, of a locomotion in a spider. And these 8 legs were not going in some kind of limit cycle motion. They're all over the place. And the remarkable thing is he took a fine pair of surgical scissors and he cut a leg off. And then watched the animal as it again made its approach to a fly. You couldn't see any difference. Now that is the great virtue of chaos. And the way in which it arises is by the vast interaction of large numbers of neurons. Now I want to show an alternative example of locomotion in an artificial animal. You know, Rodney Brooks and a number of other people have made these artificial insects which walk in a kind of clockwork fashion. This leg moves, that one holds, and so on. Coupled oscillators, limit cycle. But here's an alternative model which was developed about almost 50 years ago by an electroencephalographer. In fact, Ray Walter was the one who first identified alpha rhythm as coming from the back of the head, not the front, as originally supposed by his discoverer. He also was the one who dated discovered, I should say, the contingent negative variation. That's this slow potential seen at the vertex of the scalp, which precedes a voluntary action of a subject and tells us that, in fact, our feet already know what we're about to do before we get informed that our brains have made up their minds to do something. he now developed his ideas in terms of this machine which he called Aquinas speculatrix, and essentially demonstrated how complex behavior could be generated by a simple system. What you see here is the chaotic trajectory of this mechanical tortoise, which consists of a carapace with a single sensor which will be activated if the thing runs into an object. It has two motors, one to go forward and one to turn, so that it performs this kind of cycloid motion. Essentially, it was designed to accept a certain moderate level of illumination. And that's described in his quote down here from his book, "Moderation gives place to appetite." This beast was designed to sit in its hutch with the bright illumination where it was getting its batteries charged. Once its batteries were charged, bright light became repellent, and it moved out to find some level of modest illumination where it would bask. And then as its battery ran down, it would get hungry, so to speak, and start looking for a brighter light, and would find it back in the hutch. It would go back in and plug itself in and recharge its batteries. That style of behavior now was generated by a very simple system consisting of two motors, a couple of relays, two vacuum tubes, what you call valves. You can see them now still in museums. They were common use when I was learning these things. This simple circuit then was sufficient to produce that kind of goal-directed behavior. It is now still being done. Here's an example from Atari of the chaotic trajectory pursued by his device, which is more sophisticated in certain respects, but in fact not a big advance over the last 40 to 50 years. So that the message is that chaotic behavior in itself is not intrinsically more complicated than limit cycle behavior, and in fact in some respects is rather simpler, because it does allow you to go from a disordered state into an ordered state through these state transitions. These are some of the references. This is Gray Walter with his book on electronic turtles. Lectard did work very similar to that with Rodney Brooks and others who are active in the field. These are all listed in this book on neurodynamics. Now, we get on to brains and this question of which sensor should we begin with. I'll give you a perspective on the human brain. This comes from Bloom and Laserson, their elementary textbook on brain, mind, and behavior. You'll see here the rather typical way in which the nervous system is viewed from behind. Spinal cord coming up into the brainstem and thalamus, the eye feeding in also to the thalamus, to the geniculate, out to the cortex. And here we have the primary sensory cortex, somatosensory. Here the motor cortex, and the limbic system, seen as a kind of a ghostly image inside. This is now my perspective on the classical way in which the majority of my colleagues view the nervous system, and also the majority of cognitive scientists as a feed-forward device, where what controls the behavior of the device is in fact the input, shown by this asterisk here in the somatosensory system, feeding in to the spinal cord, up in relays to the thalamus, to the sensory cortex, then basically over into the frontal lobes where the decision is made as to what the stimulus means, that is to say, processing the information to compare it with stored images from the past, and then making some kind of decision as to what to do about it, communicating that to the motor cortex, sending it down to the motor nuclei with a side path here into the amygdala. That's where emotion is attached, you know, like paint on a car. And the resulting pattern is shift out. That's your feed forward flow. That's what's done with linear causality. And each one of these steps has been worked out in great detail in the nervous system as far as what kinds of transformations take place, all dependent on what it is that's being fed in. The stimulus provides the forms of the information, which is now going to be filtered, matched, compared, retrieved after storage, and so forth. Those are the classical ways of looking at what essentially is passive perception. Active perception looks at the same brain, but with a different perspective. We think now then in terms of a cycle, and we can break that cycle at any place, and the place to break it is not at the periphery, it's in the middle. It's to ask, where do these patterns come from which we expect, which we are looking for? The conundrum of attention. What is it we're paying attention to and why? What is it that determines the sensitivities of cortex? This is where reafference comes in. Because somewhere down in the interior of the brain, and I choose to regard this as the limbic system, however that might be defined, and almost everybody has a different definition of what it is and what it means. Nonetheless, that is the locus on which the goals of perception emerge. And when such a goal emerges as a state transition, giving rise to some spatio-temporal pattern of neural activity, that is transmitted in two directions. One direction, to be sure, is down into the spinal cord, going out through the environment, coupling by virtue of the impact of the environment back onto the brain as the way the brain has of getting input from outside. The other form is transmitted to all of the sensory cortexes, and that's where reafference comes in. Somebody yesterday mentioned about Helmholtz. Helmholtz essentially discovered this process in the visual system. It was a soldier who had suffered brain injury in the Franco-Prussian War, 1870, and had paralysis of lateral gaze. He couldn't move his eyes to look to one side. But when he attempted to do so, he reported that his visual field appeared to jump in the opposite direction. And that gave Helmholtz the clue that there was some kind of signal, what he called an effort of will, which anticipated the movement of the eye, though that the normal person could tell the difference between movement, which was internally generated, and that which resulted from movement outside. Bill discussed some of that. That conception, by the way, was shot down by an eminent British neurologist, Hewlings-Jackson, and also by a British psychologist, Kitchener, who decided, no, this is impossible. They were working from linear causality. They didn't understand the nature of circular action. And that's why reafference is only re-emerging within the last 4 or 5 decades after being buried for almost a century. In any case, what that reafference does is to modify the landscapes of the sensory cortices. Every cortex has a collection of attractors, each of which has its basin, which provides for generalization over the infinite varieties of stimuli which can give access to it. And that collection forms a landscape. And you can think of it as a collection of valleys over a rugged, like looking at the surface of the moon. The way in which the limbic system operates is to enhance whichever basin of attraction is relevant to the particular action which is being taken. That is to say, when an animal has this goal, it takes action to implement its behavior towards that goal and to shape its sensory cortices and to adjust their sensitivity optimally to that which is relevant, that input which is relevant. Now that conception of the way in which brains operate is important in respect to, again, a new perspective on how you look at brains. Now we're looking at it from a more anterior perspective, point of view. And look, what's up front? Where's the eye? It's gone. What's up front is the nose, with the olfactory bulbs feeding directly into now this internal structure, the limbic system. That's what's important. Keep in mind that the fundamental architecture of the vertebrate brain is built around vision or hearing. It's built around the nose. Why is the nose is so critically important for what it is that you eat and avoid eating? And secondarily, of course, for finding a mate and knowing what sex it is to get successful reproduction. Well, now that change in perspective is valuable because it allows us to make use of observations on animals simpler than ourselves. Because what we really need is a simpler model than the human brain to work with. And my preference, at least for pedagogical purposes, is to go to the simplest brain around in the vertebrate series, which is that of the salamander. But before I do that, I want to introduce you to a historical character in terms of this distinction between active perception and passive perception. This is a very old way of distinguishing views of how brains and minds operate. It goes back to the ancient Greeks, in particular to the distinction between the views of Plato and Aristotle. For Plato, perception was passive. You can remember perhaps his cave. He analogized us as the denizens of a cave, and all we could see was the shadows cast on the wall by sunlight, which was passing and illuminating in outline the real thing outside. And the job that our minds had was to make sense of these unreal shadows which were being cast up there for our observation, to use our reason to deduce what was actually the true forms. Aristotle said, oh, that's nonsense. That perception is an action. It's going out and probing, cutting, burning, and then getting the forms of matter and taking those in as the basis of perception. Now you can see the two fundamental points here, points of view, one in which the beginnings of perception lie in the forms which impact onto our retinas or our ears or our nose and give rise then to images which we have to process in order to come to the real thing, some abstract form. That's the Platonic view. The Aristotelian view is more biological, but still has the intrinsic premise that the forms of what we know from outside are derived by the importing of the forms into the nervous system, what we now call information intake, with further processing of that information. Now, Plato's views dominated up until about the 13th century, when this figure, Thomas Aquinas, took over the analysis of our Aristotelian publications, what survived from the translation of Arabic from the Greek were retranslated into Latin. What Aquinas did was to write down what Aristotle would have said if he'd been able to write in Latin. And in the process, he changed it And the most particular way in which he changed it was to Christianize it. Aristotle had no conception of the soul, the Christian soul, and Aquinas, of course, for him that was central. And what he conceived of is the distinction between intention, as he now coined the term, and volition, allowing that animals as well as humans have as the central core of their behavior intention. Now that doesn't appear in Aristotle. For him, biology is destiny. There's a strong determinism which runs through it. But for Aquinas, there has to be some kind of internal independence, autonomy, which manifests the freedom of the soul. And that now is what I want to identify with the capabilities for self-organization, because intent is something which arises from within the dynamics of the nervous system, not just in humans, which is, I'm going to leave that one now aside. Free will and determinism, you guys can argue about that over beer. All I'm saying is that animals have the capability of generating their own goals, and that, in fact, we can build robots which will do that too. And Gray Walter built a prototype for this, and I think he's still the best of the breed. In any case, Aquinas introduced this term intention, and by that word he meant, in the Latin, intendere, he meant reaching out or stretching forth into the world to probe it and find out what's there. Now, the way in which this takes place is not the same as in Aristotle. And this is a critical difference which is important for me in interpreting my electrophysiological data. That there is no transport of information from the environment into the brain. As Aquinas conceived it, each individual, whether human or animal, is a unity within itself, and nothing crosses over that barrier in the way of understanding, knowledge, or information, or meaning. It's enclosed entirely within itself. Instead of having the light coming from outside, giving rise to forms which are then imported through our senses, he conceived the light as coming from inside, like a flashlight on the walls of a tent. And you now probe against that wall without penetrating it, and nothing in a sense penetrates other than the indentations on the wall, so that you essentially are shaping your body to the outlines of its limits. An example of that is an affordance, where you grab an object and, as Aquinas expressed it, you assimilate to it. Now, assimilation comes from the Latin translation, or the translation of the Latin adequatio, meaning our root word adequate, which is going towards equivalence. But notice now that when you grab something, you're not incorporating that form into your body, into your nervous system. What you're doing is adapting your body appropriately to the shape of what it is that you've got and what you're going to do with it. The affordance. The difference between the Aquinian affordance and the Gibson affordance has to do with this notion of information. For Gibson, the informing essentially is the transfer and selective transfer of information into the nervous system to incorporate that for further processing. What he described in terms of resonance, that pattern had to resonate with some pre-existing circuit in the nervous system. Aquinas says no, there is no importing of information. What you get is the shape that you put your hand into and the resulting changes which resulted from your actions, which now constitutes the testing of a hypothesis of what's out there. And all you know is what hypothesis you put forward, which was endogenously constructed, and the results of the test of that hypothesis through your own actions. Another way of saying it is that all we can know is the consequences of our own actions, what we do, and the impact of that. Now, this idea has been used as the basis for analysis for at least the last century in terms of the pragmatists and also in terms of the work of Jean Piaget, who talked about his somatomotor phase of development, where an infant learns hand-eye coordination by batting things around, trial and error, learning what happens when you reach out and do something, whether you get something nice and soft like a breast or something like a hot stove. You learn from the consequences, how to behave, how to use this apparatus, which is your essentially tool for exploring into the brain. Well, that's Thomas Aquinas, and he is not widely known ever since he was eclipsed essentially by Descartes. In my view, Descartes got it deeply wrong. And I would say, put it this way, oftentimes when I have been giving a lecture on some arcane topic in neurophysiology,